So before we start, I know there were some potential questions to clarify from last time. So
thank you very much. Just a couple of questions just to clarify my own understanding from lectures 1 and lectures 2. So in lecture 1, I was looking at your the steps that you gave, the typical steps 1 through 5 that you gave.
Yes.
And so when I look at these steps, and in conjunction with the lemma that you had proved about the piecewise linear.
Yes.
So in my mind, when I look at this, I think, and this is my intuition, and you can tell me if this makes sense or not, that what the neural network is doing is really it is doing a non-parametric regression of y on x. Now, whether you can show this mathematically or not, this is a separate issue. But I give you my intuition. So you feed it some x, it gives you some y hat.
Yes.
And you optimize the parameters of the neural network by comparing y hat with y. You minimize the parameters to minimize the L2 distance between them.
Yes.
And we know from the lemma that you proved that these piecewise, that the neural network can approximate any piecewise linear continuous function.
Yes.
And assuming, and I think this might be true, that if the piecewise linear functions, piecewise linear continuous functions are dense in the space of all square integrable functions, then really, if in my mind, what the neural network is estimating as a function, as a feature, which feature of the distribution of y given x is the neural network estimating? In my mind, it is estimating the conditional expectation of y given x because it's in the, at least when you're using the L2 norm.
So I would say it's reasonable, except so because neural networks are over-parametrized, there are many ways to use a piecewise linear function to fit your data. So which way you use your piecewise linear function to fit your data is really the thing that's not clear. Which one of the possible extensions by piecewise linear functions you get. And so like, it's not enough to say you're just giving me some estimator. You need to also tell me what the regularity in some sense of the estimator is, to know that you make reasonable predictions also between data points on examples you haven't seen. So modulo that, I think that's a totally fair thing to say. Neural networks do non-parametric regression. I think that's or non-parametric classification or whatever your task is. I think that's totally fair.
And so if you change then the loss function, then the nature of the prediction changes. So if instead of
yes.
L2 loss function you were using an L1, then instead of estimating a conditional expectation, you are estimating a conditional median and stuff like that, right?
Well, I mean, maybe. The thing is, again, it's unclear what you actually get. Like, there are many ways the problem is, you can drive all your losses to 0 exactly. You can fit every data point. And so again, the question is, which way of fitting the data do you find? And that's what's not clear. That depends on the model you use and the optimizer together.
But maybe to comment on this point, so in a typical non-parametric setting, so you would basically take the O2 loss, the way you take f of xi compared to yi
yes.
in a square loss. And then typically it's a empirical risk maximization. So you typically take a class of function over which you minimize.
Yes.
F is in a certain class,
yes.
which has to be chosen carefully.
Yes.
So now just the class of functions and this is different. It's different than the classical.
That's right. It's just very big, and it's like unclear which function you choose. That's right. I think that's fair. Yes. Okay.
The second is about just the algorithmic part. So when you feed in the data, right? So you said in this steps you had data going from, let's say, x1, y1, up to, you had n, little n.
Yes.
Right? So the way it works is you take x1, the first observation, the vector of observations, you give it as an input to your network. Out comes y1 hat.
Yes.
For the same configuration, then you put in x2, out comes y2 hat, and the parameters of the network are the same between y1 hat, y2 hat.
Yes, of course.
Okay.
Mm-hmm. Indeed. So you have to use the same parameters for all data points. Otherwise, well, yeah. Yeah, indeed.
And my last question is about lecture 2.
Okay.
In lecture 2, you used the phrase no feature learning. And you had said it meant that because, we said this because theta t gets closer to the linearized version of theta t as t gets large. No feature learning.
Yeah, so for me, no feature learning means you make the same predictions as a linear model. Someone gives you a collection of features, like basis functions, and all you're doing is learning coefficients at a fixed data-independent set of basis functions.
So, okay, when you say learning, it's the coefficients of the neural network, right?
No, I'm saying no feature learning means there exists a linear model, linear in its parameters, so that the predictions you make with your neural network are the same as the predictions you get out of your linear model.
So
that's what I mean by no feature learning.
So this was my question. How would you recognize, so if you simply gave me or some other researcher y's, x's, and the y hats from your neural network, how would a researcher, just based on y's, x's, and y hats, recognize that there was no feature learning going on?
Well, I mean, it's not so trivial, but for example, there are lower bounds on the sample complexity of learning with linear models. So if you can prove that you beat those lower bounds, it means you can't be a linear model. So that's a canonical example of how you could tell that there was feature learning. So, okay. Other questions or comments about the previous lectures? Okay. Oh, yes?
Is there a relation between the no feature learning and that the benign overfitting that we mentioned during the first lecture, so the fact that we fit both the signal and noise but at different frequencies?
So I would say benign overfitting is a phenomenon that we observe both for linear models and for nonlinear models, but we've really only proved it for linear models mathematically. So it's just the idea that in high dimensions, it's okay to fit the signal and the noise. At least in many situations, it's okay. And we observe that with neural networks, but people also proved it for high dimensional regression problems. So, yeah. Okay, excellent. So okay. So for what I want to present today really, I think, is a very exciting chapter in how people study neural networks. And there's really only one idea I want to emphasize, and we'll track down some of its ramifications. But let me just kind of remind you of the basic notation and kind of set things up. So today, I want to consider a shallow network, which just means one hidden layer. And let me remind you of the notation, but also, as I usually do, introduce some new piece of notation because I can't help myself. Actually, because it's necessary. Okay, so let me write it this way. Let me introduce a parameter I'll call gamma, which will rescale the output of the network. Okay, the output of a one-layer network looks like this. I'm explicitly factoring out the dependence on the hidden layer width here, and I'll factor out the dependence on the input dimension in the first layer as well. It just makes my life slightly simpler. Okay, so we're going to consider a one hidden layer network. Before we were just considering gamma equals 1. That was yesterday. Today we'll consider a different gamma. Okay, but let me be very precise. So our optimization looked like this. We were going to optimize our parameters by gradient flow. So it turns out the right thing to do is to multiply the learning rate or the step size by gamma squared, as you will see. So eta was the learning rate we had. And you have the gradient of the loss at your parameters at time t. Okay, and then just to be precise, to complete the picture, at the start of training, the W's are IID Gaussian. Okay, so W1 ij and W2 I are all Gaussian, mean 0, variance 1 for the purposes of this lecture. Okay, so this is the kind of thing we were studying, right? So last time, when we talked about the NTK regime, it just corresponded to taking gamma equals 1, or order 1 constant. It didn't matter. Okay, there was no gamma. This is the optimization procedure we studied. This was the mean squared error over a fixed training data set, and there was no rescaling out here. Yeah. Da! What X alpha? What are you talking about, Giovanni? Okay, yeah, yeah, right. Indeed, thank you. Thank you. Yeah. This is okay. So this is what we did last time. And what we found, the kind of TLDR from last time was that you get a linear model as the hidden layer with n1 goes to infinity. Yeah. So eta is the step size that you take. It's like it's just an order 1 number. You can take it to be 1. It's not. I just leave it in there, just because I typically think of this as just a surrogate for gradient descent with a step size eta. So it kind of survives. Yeah. Okay. So this is what we did. We proved, or I sketched for you the proof, that in this kind of parametrization, if you randomly initialize your parameters to be IID Gaussian, it wasn't important that it was Gaussian, and you run something like gradient flow or gradient descent with a small step size, then if the width of the network becomes bigger and bigger, your entire trajectory of training is the same as that of a linear model. That was the no feature learning stuff. Everything becomes linear. And so we decided this was sad. I got many questions about who cares. But OK. So today, what I want to do, let me write it up here. OK, I can't help myself. I'm going to write it over here. Yes, of course. So I rescaled the, yeah, indeed. So I said CW equals 1. It doesn't matter for one layer networks. Yeah. Everything works out a little bit better when you scale this way. It's not. OK, so today, I'm going to take gamma to be the square root of n1. OK, it seems like a totally random choice. So the outputs of the network are going to be way scaled down. And we're going to see that we get a completely different answer as we take the width of the network to infinity. As n1 grows, we're going to get interesting things related to Wasserstein gradient flows. Okay, I'll explain what all that means, at least more or less, later. But you get things that are related to optimal transport type dynamics. You very much don't get linear models. You get a completely different scaling limit of neural networks. And I think it's kind of fascinating, and I hope to have time at the end to come back to it, to explain in some mechanistic sense, like, why just rescaling the output could cause such a big difference. Okay, I'm not going to dwell on it at the moment. So for me, I just have a 1 over n1. That's not totally crazy. It's like just normalizing this sum. It kind of looks natural if you don't think about it. OK, so this is called the mean field parametrization or mean field scaling. OK, that's the goal for today. OK, so is this clear what we're trying to do? I know it's not clear why this makes any difference, but it makes a big difference. That's going to be my claim. OK, very good. Very, very good. OK, so what are the 3 things I hope you learned today? Or more precisely, the 3 things I hope not to say in such a complicated way that it's impossible to understand them. OK, so the first thing is that there's a simple but kind of deep and beautiful and useful way of reformulating everything about these mean field neural networks in terms of optimization in a space of probability measures. OK, so mean field neural networks, I'll explain in just a moment, are basically all about, what did I want to say here? So learning in the space of measures, space of probability measures. Okay, I'll explain how that works. But there's kind of this dictionary between one-layer networks in this mean field parameterization and probability measures, and all the questions of what the learning does can be transferred over to dynamics in the space of measures. And that's where we get things like optimal transport. That's where that naturally lives. Okay, so the second thing I hope to convey is a kind of amplification of this point, or I didn't spell learning right, apparently. A special case of this, but one that's useful. So I'm going to give you a very short derivation. It'll be formal, but it's possible to make it totally rigorous. That when you take the hidden layer width to infinity in the mean field scaling, then what gradient flow actually corresponds to on the parameters is exactly Wasserstein gradient flow. You get L2 Wasserstein gradient flow on the space of measures. Okay, so this is a complicated and interesting set of PDEs, if you want, that I'll kind of remind you or tell you if you've never seen it, are like ways of formulating many, many things that you've seen potentially in different contexts. Okay, so somehow gradient flows with respect to Wasserstein geometry are fundamental objects. So it's like a connection between mean field neural networks and something else that's complicated but well studied. Okay, and the last thing that I hope to say, and it's really a reformulation of point number 2, but it's still kind of different for me, is that at least when the depth of the network is 1, which is the only thing I'll consider in the lecture, mainly because no one knows how to do things for deeper networks. But that's not totally true. There's like exactly one human computable formulation of how to do things for deeper networks, and it's beautiful. And there are basically every question about it is still open, so I'm not really going to present about it. So, but in this case, mean field neural networks are really the same thing as, like, if you want to think of it this way, very simple McKean-Vlasov systems. If you don't like those words, maybe you like interacting particle systems. Okay, there's a lot of ways of saying it, but they're connected to very basic and kind of well-studied models in mathematical physics. Yeah.
The Wasserstein metric, is this when you compare quantile functions? So it is a distance?
No, so it's slightly different. It's about transport costs. But I'll introduce it. I'll define it. Yeah. Sorry, just so you kind of know where I'm going. These are like the three things I hope to kind of touch on. Okay, very good. So in fact, let me stop. So I have to write one more thing that I hope never to erase. So, but it's a good time to pause. Yes.
So it seems that like you are shrinking to zero the output.
Yes, correct. So the way it works is you're going to initialize your prediction to be 0, but your gradients will be non-zero. So your
it's a gradient because of the gradient because you are changing the gradient also.
Yes, precisely. So if you want to think about it in some geometrical way, what you're doing is you're initializing near a saddle point, but you're taking a large step size so that you escape in finite time. That's right. So you'll see that this is the right scaling. It's not obvious till you do the calculation. But they're just rather different kind of things in retrospect. It's just they don't look different when you write it this way. Yeah. Other comments or questions? Okay, so here comes the idea. In some sense, it's such a simple idea that it's kind of easy to scoff at it. But I think it's quite a beautiful idea. So the idea is that you can write any one-layer neural network with this kind of parameterization in terms of a probability measure. Okay, so we can write z2 of x and theta as, okay, so this is a good opportunity for the graduate students, okay, if you've never seen this. Like, it's good to take 30 seconds of your life and think, how could I possibly rewrite the output of this mean field neural network using some kind of probability measure? Okay, it's an underspecified problem, but all of machine learning is underspecified, so you got to get used to it. Like what am I even talking about? What? Okay, what counting measure over what? Aha, okay, well, thank you, Mr. Graduate students. No, that's great, that's exactly right. Okay, the idea is not mathematically deep, but it's hard to realize that it's a useful thing at first, right? The output is just an average when gamma is equal to square root of n1. And so you can just write the average as an integral. Okay, so you get an integral of, I'll write it this way, w2 times sigma of w1x against, I'll write it this way, d mu theta n1 of w1 w2. Okay, this is an integral over r n0 plus 1. So I didn't quite say this, but as usual, just to make my life simple, my output is always a scalar. You can do this in any output dimension you want, obviously. But okay, and what is this measure? This is just the counting measure, right? Mu theta n1, I hope I put the n1, I did, is just the empirical measure. I goes from 1 up to n1. If you want to say it this way, and I do, over the configuration theta I of the ith neuron. In other words, the weight you get here and the weight you get here. Okay, where theta I is nothing more than w2i and 1 over root n naught times w1i. Okay, so that's not a very profound mathematical theorem, but the point that I want to make is just sitting before your eyes is this map. Every neural network with one hidden layer you can rewrite as a probability measure in the space of the weights going in and out of a single neuron. So if you're not going to send the input dimension to infinity, this is like a fixed space in which you can work. And the thing about taking the width large or understanding what happens at large n is just the width of the network controls the number of atoms you can have in this probability measure. Okay, so what's going to happen as the width grows is your probability measures are going to be allowed to be continuous in the limit, right? Because you're going to have infinitely many atoms. But that's kind of going to be the effect of infinite width. Okay, very good. So this is kind of nice. I will often forget this normalizing factor because I'm not going to scale the input dimension. So excuse me, don't yell at me too much. Okay, you can yell at me all you want. It's okay. Okay, very good. So let me put this up top and see if there are any questions or comments about this, because I want to kind of give two applications of this idea. The first application is the first chronological one, and it's the easy one, and then I'll talk about optimization, which is slightly more complicated. Is this okay? How happy is Ivan? That's my main metric. Okay, very good. No, okay, well, no, but that's why it's my main metric. I never said I want to make it hard on myself. You know? Okay, so very good. Okay, so here's application one of this idea. So this is an application to doing approximation theory with neural networks, with one-layer neural networks. So this goes all the way back to the 80s. So I'll present, okay, like always, I'm going to lie a little bit. I'm going to smash together like probably 50 different theorems, but I'm just going to call them the theorem of Sabenko, I think in 89 or something like that, plus. There are lots of other papers, and I'll kind of smash them all together. So this is called the universal approximation theorem. Okay, many people have heard of it, but it doesn't matter. It's exactly what it sounds like. So let me be very careful. Okay, so the theorem goes like this. So you fix the input dimension, and you fix any function sigma, your nonlinearity, that's non-polynomial. Okay, so a lot of sweat and tears went into the most general possible sigma you can have. And I think the best result I know is you can take any sigma for which there exists an interval on which it's not a polynomial. Okay, it doesn't matter. Just think of sigma as something nice. Okay, you have a nice nonlinearity. So then the following is true. Sorry, let me actually fix one more thing. Let me fix to make my life easy, a compact subset of Rn0. Okay. So then, for any f, a continuous function from omega into R, what do we have? Okay, so there exists a width, for any f, oh my god, and any epsilon, there are too many quantifiers. There exists a width and a setting of parameters. So if you count the dimension of the parameters, I think I counted it right, I get n1 times n0 plus 1. Okay, such that the function f minus your neural network, viewed as a function of x, in the C0 topology on omega is approximated to error at most epsilon. Okay, so if you want to be very precise, this is at least one version of what's meant by universal approximation. Any reasonable function can be arbitrarily well approximated by a sufficiently wide neural network. Okay, great. So there are many different kinds of proofs of the universal approximation theorem, but I'm going to give you the simplest kind of proof. Okay, and I'm not going to give you the full proof. I'm just going to give you the idea of the proof. But really, it's like a two-line proof once you buy this kind of integral representation story. So I think it's a nice proof. And that's why I quote Sabenko. I'm basically giving his idea. I shouldn't take too much credit for it. Okay, is it clear what the theorem is? I'm going to sketch this proof, but yeah, please. For L? Sorry, L is 1 for me this whole lecture. So this is, we're back in the 1980s. It's hard to imagine. But we only study one hidden layer network. So all of today, L is 1, yeah. Okay, very good. So here's the proof. The proof has 2 steps. So step number 1 is like this. So maybe I'll call this like approximation by infinitely wide networks. Okay, and this is really where the assumptions on sigma all come in. So if sigma is nice, in particular it's not a polynomial on some interval, what you can prove is that for any f, you can represent it as an integral of some measure against your particular sigma in the way that I've had before, d mu f of w1, w2. Okay, so the statement is there exists a measure for which you can do this. Okay, and it's not completely crazy. Like, the sigma I like to think of is, imagine that sigma is like sines and cosines. Right? This is just saying that you can basically represent f as a Fourier series. Okay, or think of sigma as like the indicator of a half space, or like, like a step function. Then this is basically saying you can write any function as like a sum of scaled indicators of half spaces. Okay, for that, I need to turn on the biases. I have to be able to shift around the half spaces. But it's not such a crazy statement, I think, to believe. Okay, so once you believe this, so I call this approximation by infinite width networks, precisely because when you look at this way of rewriting your neural network as a measure, the constraint that you were at finite width just constrained the number of atoms. So if I'm at infinite width, I don't have any constraints on my measure. I can take any measure I like. Okay, so, and indeed, this measure here, it's not even necessarily fully constructive in a sense how to get it. It just exists.
This measure now depends on f itself?
Yeah, so I'm trying to approximate a particular f, and so I want there to be a particular neural network. Right? So say there's some f, and now, so now I get some measure mu. Okay, so now, okay, again, a question for the graduate students or, lifelong graduate students or whatever. How do I finish the proof? Yeah, okay, great. Okay, so I keep trying to fool Mark, but it's not possible, seemingly. Okay, so the point is, like, all you have to do now is take this potentially continuous measure and just approximate it by a sum of delta functions, and you're done. Okay, so for all mu f's in the space of probability measures, okay, any reasonable probability measure you want, certainly on a compact set, though it doesn't matter, you can just say that mu f is approximately equal to the empirical average of draws from mu f, delta theta I, where theta I are drawn IID from mu f. Okay, so that's done. Modulo some like details. And that's the whole proof. Okay, so somehow in this, from the point of view of the approximation theory, the translation between measures and functions just lets you separate the question of, can I represent my function using the nonlinearity at all, using infinitely many neurons? And then how well can I approximate this limiting measure by something with only a fixed number of atoms? That's kind of the two questions you have. And okay, so maybe I should give some credit. So this idea, believe it or not, was really first used in a paper of Andrew Barron. So he had a pretty famous paper where he invented these things called Barron classes. Doesn't matter. There was a nice paper of Andrew Barron where he used this kind of procedure to get like uniform rates of approximation over some interesting function classes.
Isn't there some element of circularity here? So you're trying to approximate mu as a sample average of these measures, and then you say that theta i's are IID draws from mu itself?
But I'm just saying, the question is, does there exist a neural network that approximates? So if I use this thing, that's going to give me a finite neural network. And so as long as this finite neural network approximates my particular mu f, that means if I had just replaced this mu f by my finite thing, I get a way of approximating f by a neural network.
So you don't want to say that theta I is drawn from delta theta I. That doesn't make sense.
No, I just want to say, like, I just make n1 IID draws. And I use this neural network that I get. No, it's not a constructive approach, but who needs constructive approaches when you can save Blackboard space? Fair enough. Yes?
Or just because, so the assumption of sigma are the one written there, not continuity, nothing.
I believe it's just measurable, and there exists an interval on which it's not a polynomial. I believe that's the latest thing that I ever saw. Is like, look, yeah, like the original paper of Sabanko assumed that sigma was what he called sigmoidal, that at negative infinity it's 0, and then it can basically do whatever you want, and then at positive infinity it kind of plateaus to 1. That was the kind of thing he did, but that was just some special case to make this part of the analysis easier. You can rescale this thing to be an indicator of a half space, but yeah. Indeed. Yeah. So this is just the C0 topology. So it's just the soup of the differences over all the, yeah. So if you want to control it in like some derivatives, you just need some derivatives on sigma. Otherwise, okay, your function's not differentiable. Yeah.
Is there some easy way to understand why polynomials are bad?
Yes, there is. So if sigma is a polynomial, you can never, like you just start taking linear combinations of polynomials of x of a fixed degree. You can never, never get anything that's not a polynomial of that degree. Right? Like if sigma of x was like quadratic, then no matter how many neurons I have, I just take linear combinations of quadratic functions, and polynomials form a vector space, so they're closed under addition. So I just have to be able to escape any polynomial subspace. That's kind of the, yeah. Well, it depends on sigma. No, if you want to make sigma ridiculously general, like some people want to make it, you're going to have a ridiculously non-constructive UF. So if sigma is literally just, a step function like this, for example, okay, then you need to add biases, but then the kind of functions you're using are just indicator functions of half spaces that you're allowed to take linear combinations of. And so it's just a kind of classical approximation thing that you can approximate any function by linear combinations of half space indicators. So it depends on how concrete you are with sigma. Yeah. Okay? Any more questions or comments? Okay, so this is kind of like version 1.0 of this idea, but okay, approximation theory is interesting, but it's like not the main thing. The main thing is what the heck do you learn, and can you describe the training dynamics? Okay, so that's really application 2, and that's going to take the rest of the time. Okay, so application 2 is optimization. Okay, so the idea is like this. You have this optimization procedure, which I put on the board here, and that's a dynamics on the space of parameters. That's how we define it. But now for any setting of the parameter vector, you get some probability measure. So you can ask, what's the induced dynamics on the space of probability measures? That's the question I'm going to try to answer. And so here's the theorem. Okay, maybe I should say it's a lemma. Okay, but you'll see. Okay, so let's fix for the statement of this theorem, although you don't actually really have to. Let's fix a training data set that we're interested in, that we're going to have to fit. Okay, and suppose, and this is really the only assumption that we need. So I didn't even tell you the form of the loss function that I'm going to be trying to minimize. The only thing I want to know about the loss function is that it depends on the parameters only through the values of the output. So L of theta actually depends on theta only through these mu and 1 of thetas. What did I call it? Oh my god. Sorry, that's not how I wrote it. Mu and 1 sub theta. Okay, so an example of this is any empirical risk. Like the sum of the squares of the differences, so e.g., if you just took the sum on I goes from 1 up to n of, okay, maybe I'll put a 1 over 2n just for fun here, z2 of xi and theta minus yi squared. Okay, that's a perfectly good example. And the reason that these empirical risks only depend on the empirical measure of your parameters is that they only depend on the parameters through the output of the network. Right? And the output of the network only depends on the empirical measure of the parameters. So that's what I mean. And the kind of thing I'm excluding is adding an explicit regularization. Like if I were to add lambda times the L2 norm of the parameters squared, that's okay. That's a sum over all the parameters. But if I were to add something more complicated, maybe I can't accommodate it. Okay, so my main assumption is that the risk I'm trying to minimize depends on the parameters only through their empirical measure, which is the case we almost always have in practice. Okay, so then I claim there's a very clean way of rewriting the training dynamics you get on the space of measures. So let me write it, and I'll kind of discuss it, and then I'll give you a formal proof of it, because I actually wasn't able to find a good proof of this anywhere in the literature, at least not quite like this. So if you ask, what's the dynamics on the space of measures? Okay, so now I'm asking not how the theta t's evolve, I have a formula for that, but how the mu sub theta t's evolve. Okay, let me write two different formulas for it, which are the same formula. So minus eta, so one explicit way is you get the divergence of the following kind of vector field. So you take your probability measure and you multiply it by the gradient of the variation of your loss with respect to your probability measure. Okay, so it's a little bit cryptic, but let me just say it in a slightly different way. This is just minus eta times the gradient with respect to the Wasserstein 2 geometry, which I'm going to introduce in just a moment, don't worry, of this loss function L, which is now just a function by assumption. Oops, this should be theta t. Of the empirical measures that you have. Okay, so what I'm saying, the content of this theorem is that for virtually any loss you're interested in, the dynamics in the space of measures you get is the following. So I'll explain what it is in more detail, like I said, in a second, but the space of probability measures is an infinite dimensional space. Okay, and there are lots of different ways to put a geometry on it. But one of the most kind of important ways these days to do that is this Wasserstein 2 geometry. There's some particular way of essentially turning the space of probability measures into a Riemannian manifold. Okay, and then what you're doing is you're just doing Riemannian gradient descent for this particular Riemannian metric you have on the space of measures on the loss function L as a function of your empirical measure. Okay, that's like the entire statement of the theorem. So okay. And if you want the definition, or like one classic definition of the Wasserstein gradient is exactly what I wrote here. But it's a little cryptic if you've never seen it. Okay, I'm going to show you formally how to derive it right now. It's just a couple of lines. Okay, so I'm going to erase. I'm going to let people digest. And I'm going to take questions, and I'll show you this derivation. I want to show you the derivation of this theorem, the purely formal one. Because like I said, I actually couldn't find it anywhere in the literature, although there are a million papers that implicitly kind of do it. They all do it in some seemingly special case. I'm sure all those authors know this to be true. I didn't know it to be true.
It's always all of the measures or just over the point-wise, over the ones that are supported over endpoints?
Yeah, so here you see it's defined for any measure you like because no, but this z here is simply the integral of some function. Let me put it that way: phi of x and some parameters w1 and w2 against the measure d mu of w1 w2. So you see, it's just so phi is fixed. It depends only on your nonlinearity. And it's just a functional of this measure. It's a very simple-minded functional. It's just a linear functional of the measure. So in this way, this is a perfectly well-defined function for any measure for which this integral makes sense. Yeah, so that's kind of the sense in which I'm like moving to the space of measures. I no longer think about the neural network directly, except for as like some way of defining my dynamics originally. So okay, that's a great question, and the short answer is it doesn't escape. But it wasn't completely obvious to begin with. It just doesn't. Yeah. Yeah, that's true. Okay, is this okay? So yeah, just bear with me for a second. I'm going to explain. I'm going to try to give you some like small crash course on what this is supposed to mean. But let me just show you the derivation to show you that there's nothing magical, at least formally. Just use the chain rule. And then you close your eyes.
Do you need the positive curvature of that space? Or can you use a hyperbolic space for Lobachevsky?
So you'll see. Here's the basic point. So you might ask, where does the 2 come from in the Wasserstein 2? So it comes from the fact that when I first defined my gradient flow, I used the L2 gradient. Okay, so that's the connection. And I don't actually know enough about Wasserstein spaces with curved backgrounds to know whether what I write is just going to work out of the box or whether there's other corrections that come from curvature. I'm actually not certain. Yeah. So maybe you can tell me after you work it out. Okay, very good. Let's do the proof. Okay, the only kind of proof I know how to do, the kind of purely formal proof that they used to teach me as a PhD student because they knew I wasn't capable of doing the informal proof, seemingly. Okay, so let's try to do it. So let's try to compute the derivative of this probability measure. Okay, so how do you compute the derivative of a functional of your dynamical variables? You have to use the chain rule. Okay, let's do it. Right, so the dynamical variables are the theta i's. So you sum over all your dynamical variables, and you get the gradient of your thing you're interested in with respect to the theta I. Remember, this was the weights in neuron I, and this is at time t of the measure, times the derivative of the theta it. Okay, you got 3 out of 10 points on the exam. That's how I think about these kind of calculations. Okay, now you have to use the definition of this thing, so we have that up there. Maybe that's not how you guys do it in Europe. Maybe you're more harsh with your grading. But in the US, if you put your name on the exam, you're already kind of getting 10 points. Okay, so I keep this term, theta t, and then here I get minus eta times n1. And I'm using here that gamma squared is equal to n1. And you'll see why that's important. And then I have to compute the gradient with respect to theta it, with respect to theta I, evaluated at theta it, of the loss at theta it, or theta t.
Should you put parentheses around the first gradient after that?
So, sure. I put parentheses wherever you want. Okay, so far so good. And now what's the key point? Right? Now the key point is I have to simplify this term, and I have to simplify this term, and I'll be done. Okay, so you should understand this in a distributional sense, right? This is a probability measure, and I'm taking the partial derivative with respect to the ith thing that it's over. So when you think about that for just a moment, what you get is ultimately you get the gradient with respect of theta evaluated at theta equals theta it. Maybe I'll say theta I. Theta it, and you get a 1 over n1 to come out. That's what this term is, right? Because this thing is just 1 over n1 times the sum of the delta functions at all the theta t's, but you're only differentiating with respect to one of them. Very nice. Then I keep the minus eta n1. And then over here, I just have to use the chain rule again, right? The loss depended on the parameters only through the probability measure. So I take the variation of the loss with respect to my probability measure, mu n1 theta t. And then I have to take the gradient of this thing. Okay, so I take the gradient with respect to theta I at theta it equals theta I. Okay, very good. And then, again, because this is only with respect to one of them, you're going to get kind of a 1 over n1 that comes out. Yeah, very nice. Okay, and then I just collect everything and I declare victory. Right, so one n1 cancels another n1. This n1 normalizes the sum, and this is the gradient dot the gradient of this thing. And I'm taking the sum over all the theta i's. So I get minus eta divergence of mu n1 theta t times the gradient of the variation of the loss with respect to mu and mu n1 theta t. Okay. So if you've never seen these things before, this is like total gibberish. So just ignore it. Okay, but the reason to show this is just that it's only 4 lines of derivation to prove this kind of result. There's almost no content to it. It's just a very abstract statement that if you have a loss that depends only on the empirical measure, and you are optimizing the parameters using L2 gradient descent, then what you're really doing on the measure is Wasserstein gradient flow on the functional L that you were trying to minimize. Okay, that's kind of all there is. So you can just delete this from your mind if it's not interesting, but I know there are some experts in the room, so I thought they might find this to be fun. Okay, so let me just pause for 1 second. The next thing I'm going to do is I'm actually going to tell you about these Wasserstein gradient flows and try to actually explain why this is a significant thing to know, even if you don't care about these kind of derivations. Okay, so I promise interesting information is coming as opposed to these formal calculations. Okay, are there questions or comments about this? Where are you? Mark, what do you think about this?
I'm not used to this notation. It's okay.
Okay, but did you know this fact? I'd never heard anyone say it. If you have a bunch of parameters and you're optimizing them by L2 gradient descent or gradient flow in the space of parameters, but the objective only depends on the empirical measure, that you automatically get Wasserstein gradient flow on the empirical measure, or on the space of measures.
I can tell you if you prove some statistical result with making Lasso, this type of variation with respect to mu appears, but it has nothing to do with your calculation.
Okay, I see. So I just think that's a useful thing to know. Anytime like things depend on empirical measures and you're doing L2-based gradient descent, you have Wasserstein gradient flows. I just like didn't know that. Again, I think some people know it, but like I just had never seen it phrased in quite this way.
But also, in respect of making lots of confusion, say that what you write delta L with respect to delta mu, it has a meaning. So it's
Yes.
a definition.
Yes.
Proper.
Yes, it does.
It's not an abstract. It has a particular difference.
I completely agree. It's just the dependence on mu is so simple-minded in my case. It's all only via linear functionals of mu. So the derivative is exactly what you think it is. It's only for more complicated, so that's why I kind of don't specify it. Yeah.
It looks like in the last lecture and this one, you seem to be deep inside looking at the same sort of structure of some parameter, which is the N1 going to do it in different ways. But what information you capture in this one that you don't capture in the session from yesterday, vice versa. So it looks like it's going to give you information about something about learning yesterday versus today. What
So the point is this. Although it seems like a minor change, the change is so complete and total that you will get completely different answers for what you learn. It's kind of like, what's a good way of saying it? It's kind of like investing with interest or without interest, without like reinvesting your returns. It might seem like a small difference, but like in the end, one goes to infinity and the other doesn't. Okay, or maybe they go at different rates. This kind of thing. Okay, I'm happy to answer that question a bit later. You're going to see what comes out. Okay, but I promise that this dynamics is somehow, in the limit as n1 goes to infinity, the two dynamics are completely different from each other. That's just kind of the main point. It's subtle, but there are different infinite width limits you can take for these neural networks. Okay. So let me not say any more about that at the moment. I promise I'm happy to come back to it. But I want to say something useful to most of the people, hopefully, in the audience, which is what the heck this kind of result buys you. Imagine someone just tells you that the dynamics you get on the space of empirical measures is just called Wasserstein gradient flow. Forget about any derivation. Like, what the heck does it mean? So just out of curiosity, who here already knows what a Wasserstein gradient flow is? Okay, some people do and others don't. Okay, so this is great. Okay, so let me go slow. So let me start with the definition, which probably most people have seen, but maybe not. Okay, so suppose you're given two probability measures, mu and nu. Sorry, I'll write it this way. They're probability measures with finite second moments, I'll be careful, on some space RD. Okay, so the way I think about them, I can only really draw a one-dimensional picture, so here's RD. And I think about, this is like some classic, okay, you've probably seen these pictures, but I like them, so I'm going to draw it. It's like some kind of classic transport problem, okay? You have a probability measure mu, and this measure mu is like, there's a bunch of dirt here. Okay, this is like telling you how much dirt I have at every place. And then the probability measure nu, I draw the opposite way. Okay, this is nu. And there's a hole, and it tells you how deep the hole is at every point. Okay, and my goal is going to be to transport the dirt from mu, there's exactly volume 1 dirt, and fill this hole, which has volume 1 because they're probability measures. Okay, so I'm going to tell you something about that, and that's going to give you a distance between mu and nu. Okay, it's called the Wasserstein 2 distance. So the Wasserstein 2 distance squared between mu and nu is written exactly like this. Let me scoot this up for a moment. Okay, so it's the infimum over all joint distributions. So pi is a probability measure, second moments on RD cross RD. And pi has as its marginals mu and nu. So the first marginal of pi is mu. The second marginal of pi is nu. And then what you infimize is the integral over R2D of x minus x prime squared d pi of xx prime. Okay, so pi is like a transportation plan. Pi basically tells you what proportion of the dirt at x do I transport to the point at x prime. That's what pi is saying. And this is the cost of doing the transport. This is why it's called the Wasserstein 2 thing. 2 just means that my cost is quadratic in the distance between x and x prime. Okay, so what this definition is saying is this is some way of trying to define a distance between two measures, mu and nu. And the distance is what's the most efficient, what's the most cost-effective way to transport the mass of mu onto the mass of nu. Okay, that's what Wasserstein geometry is kind of about. It's about these kind of classic transport problems. Okay, okay, this is a somewhat abstract definition, but I think it's kind of the most transparent one in a sense. And there's a long, very long, okay, almost infinitely long line of work that basically has been studying what happens when you actually understand the space of the space of probability measures. With this right now, this is like a distance function in the sense of metric spaces that I've put on it. Okay, and so it turns out to be a very deep and interesting area, and I'm going to not do it any justice by telling you the moral of the whole kind of development of these gradient flows and metric spaces and all this in one sentence.
So the two appear in two places on the left, and there's subscript and
So this is just the definition of the square. So sorry, the upper two is the usual two. Maybe it wasn't obvious though. Yeah. Okay, so here's the moral of this whole thing. So here I have the space of probability measures on RD. So this is P2 of RD. And I just gave you a way to make a distance between two measures. You have to believe me that it satisfies the axioms of being a metric in the sense of metric spaces. It does. Okay, so the moral is that this metric, this W2 metric, is actually the distance function corresponding to a Riemannian metric from, okay, at least a formal infinite dimensional Riemannian metric. Riemannian. Is that how you spell Riemannian? Am I crazy? Okay, it doesn't look right for some reason. Riemannian metric, which I'll call maybe GW2, with non-negative curvature. Negative curvature. Okay, and so not only is this just some distance function between metrics, it's actually the distance function that comes from a Riemannian metric. There's a much richer structure that underlies it. So in particular, you have notions of geodesics, you have notions of gradients and everything. Okay, and the gradient with respect to this Riemannian metric of some function defined from the space of probability measures to R, so I have some loss I'm trying to minimize, is exactly this formula that I gave you before. Okay, it's the divergence of the measure mu, so at mu. Mu times the gradient of the variation of L with respect to mu. And okay, as Mark obviously correctly points out, you sometimes have to be careful defining what you mean by this thing. Okay, but I'm not going to be too careful. I'm just saying there's some usable formula for what the gradient, the Riemannian gradient is with respect to this Riemannian metric. Okay, everything becomes hard because infinite dimensional Riemannian geometry, and so it's not even clear what I mean. I mean, but okay. So I'm not an expert in it. I only know that it's a beautiful subject that has attracted a lot of attention and so on. Okay, so I want to give you some examples of why people consider this to be such an interesting mathematical gadget of what loss functions L or what objective functions L correspond to various things you secretly know, but by some other words. Okay, I'm going to give you some examples of what gradient flow with respect to the Wasserstein metric actually does for you. It unifies lots of things in PDE and machine learning and so on. Let me just stop for 1 second and ask if there are questions or comments about this. Yeah.
The notation, right? The L and the mu, is that the notation of linear functional derivative?
So the short answer is you have to be careful to define this, but roughly like this. Okay, you might ask, what's the tangent space at a element? Okay, it's a little delicate, but if mu has a density, it's a nice continuous object, then you can just think of this tangent space as being L2 of mu. Okay, so elements in the tangent space are just functions. So like, if L is just a linear functional of mu, the integral of some function d mu, then this derivative is just that function. So this is now a function of your kind of configuration variables, and I can take its gradient with respect to like the d, like this d is remaining finite. That's this gradient. then I multiply it against my probability measure, and I have to take, in the weak sense, the divergence of this vector field. Oh, I see. So the short answer is I don't know how to answer your question. Yeah, that's just the truth. All I know is just in special cases how to compute this, and it's like, yeah, it's not completely clear to me how to say the most general version of this statement. Yeah.
I will be thinking of the measure as the theta, as the parameter. The measure that you're moving, I should be thinking of it as a boundary.
That's right. So right. Yes.
Who's responsible in the model for the fact that you can think of it as something that lives in the Wasserstein space? So what prevents it from taking to something crazy that escapes the longitude?
So I'm not sure what to say other than, you see, the formal derivation, which I thankfully erased so we didn't have to look at that eyesore anymore, is formal and works at any finite width. It works, it doesn't require any kind of asymptotics. And what I would say is, in retrospect, it's just the structure of the problem you're studying if you think of your neural networks as being measures. Your optimization is just someone tells you do Wasserstein gradient flow. That's your objective function. That's like your learning procedure. That's all it is.
No, I am comfortable with the fact that it is a measure, but the structure of having two moments is what if the measure, for some very pathological reason, stopped having second moments?
So if your measure stopped having second moments, then let me think for a second. So okay, then for example, if your loss were just the one that I always think about, the square of the differences, right? Z2 of xi and theta minus yi. This wouldn't even be well defined, at least on average, right? You need two moments of your measure to exist to compute the expectation of this. And so it's fair, you could ask, what if my loss was more regular than this? And the short answer is I'm not sure what happens. That's just the truth right there. Yeah, I haven't thought about it. It's like an interesting question. So I always think of this example. So I think of there as being at least two moments that I need. So, but this thing here, if you just look at the definition, this basically requires that your measures have two finite moments to even make sense of.
So you cannot replace the two inside this by one?
No, this two here, you can, but this two comes from the fact that when we did gradient descent, we did the little L2 gradient of the loss at theta. So this two is this two. So you could try to change this, and I don't know what happens when you change this. Of course, when you define Wasserstein metrics, in general, you can put a P down here, and that corresponds to putting a P up here. Okay, so that's perfectly legitimate, but I don't know what the machine learning interpretation of that is for neural networks. I'm not sure how to say that. Yeah.
Is there a convenient analytical expression, say if you have a joint density formally, then the formula for the Wasserstein distance that you could plug it into a computer?
No. Absolutely not, except in the case of transporting Gaussians to Gaussians, basically. So the point is there's a whole world of people who work on estimating pi that computes this infimum, usually from samples of mu and nu. And in general, computing pi is hard.
Even with a known bivariate copula, it will still be hard, right?
Say again?
Even with a known bivariate copula function connecting these two distributions.
Yeah, the short answer is, okay, I don't know all the literature on it. What I know is that if mu and nu are Gaussians, you can explicitly write down what the pi is. It's a very simple kind of, it turns out it's like linear dynamics that transports the mean to the mean and kind of moves the covariance to the covariance. And beyond that, I don't know of any systematic places where it's easy to write down what the distance is and really kind of what the geodesic is with respect to this metric between the two. Yeah.
If you have a concrete copula, then you're not minimizing over all joint distributions. Maybe you can handle
No, but sometimes what happens is it turns out that to transport a Gaussian to a Gaussian, you only move through the Gaussians. So it's like your ansatz kind of remains. But in general, you're right. I mean, just because you have a parametric form doesn't mean that the optimal map between them maintains it. That's right. Okay, very good. So let me give some examples. I promised some examples. Then I'm going to come back to some actual math, hopefully. Or not actual math, but like concrete neural network math. So here's some examples, which I think are exciting. So here's a canonical function you could take on the space of probability measures. The metric entropy, the integral of mu log mu. Okay, that's comes up all the time. So if you then ask, what is gradient flow with respect to the Wasserstein metric for this object? What are the dynamics on the probability measures mu that you get? Well, it's very beautiful. You just get the heat equation. So it's like, I think people were excited when they realized this. The heat equation is actually just a gradient flow on the space of probability measures. So that's kind of a beautiful statement. Okay, so how about one order of magnitude more complicated? Now I have not one measure, but I have two measures. I kind of have mu and I have a reference measure nu. And what I do is I do the relative entropy. So I'm kind of trying to go from mu to nu. Mu over nu, d nu. Okay, so then what it turns out is you get, well, of course you get a Laplacian to come out because you get the metric entropy, or the differential entropy, or whatever it's called. I don't know why I said metric entropy to come out. But actually what you get is this. You get a Fokker-Planck equation. So you get minus the gradient of mu with a velocity field, which is the gradient of the log of nu, plus the Laplacian of mu. Okay, so if you just think of nu as being e to the h, or maybe e to the v, that's a typical way of thinking of the potential, then the log of nu is just v, and v acts as the vector field that you're trying to push along. Okay, so people have studied Fokker-Planck equations forever, and Fokker-Planck equations are also just gradient flow on the space of Wasserstein, with respect to the Wasserstein metric on the space of probability measures. So that's like a beautiful thing. And then just in this context, let me just restate the neural network result. Okay, so if L of mu is what's called the kernel mean discrepancy, okay, so it's this one, you take some probability measure from which you sample the x's. So it could be the empirical measure on your training data set, or it could be a population distribution. It doesn't matter. And what you do is you take the integral over Rn0 plus 1, so I'm going to write it out explicitly, W2 sigma of W1 x, and then you have d of mu n theta t minus, maybe I'll put theta here, minus mu, some mu star that you care about, squared. Okay, this is just some silly way of writing the empirical mean squared error over a training data set if this distribution P is just the uniform distribution over a training data set. Okay, and this thing is called the kernel mean discrepancy between these two measures. Then what you get is that dt mu is optimization of one-layer networks. Okay, that's like how this result that I was presenting fits into some broader scheme. Okay, so it doesn't necessarily make it easy to analyze this gradient flow. Okay, Wasserstein gradient flows are complicated. They're like PDEs in infinite dimensional spaces, okay, at least formally speaking. But it fits into a kind of rich mathematical literature for which we have a lot of tools to say things. Okay, and I'm going to give you the simplest illustration of what to say. It's like, okay, I'm going to erase this and I'll ask for questions. And then I'll give you a hint of the kinds of results that one can more or less for free get from this observation. Okay, if you know something about Wasserstein gradient flows. Okay, is it clear kind of what I'm writing? Like the list goes on and on and on. Many things you know and love. Porous medium equation. Okay, other equation.
So you have mu n of 0 in the second line minus mu of what?
So, sorry, I shouldn't have put the theta here. Sorry, I mixed my notation. So you have some fixed measure mu star. Sorry, some fixed one, and that's the one that generated the y's from your training data. You know, this is the thing I used to call mu f. So maybe I should write it mu f. And this is called the kernel mean discrepancy between the two of them with respect to this, like the feature map, the kernel corresponding to this feature map. This is some like phi of x. Okay. Right, thank you. Other questions or comments? Is this okay? As okay as it's going to get? Oh, God. That's kind of the truth right there. Okay, so what's like, so here's a key result about Wasserstein gradient flows, which is extremely useful. It's basically just Gronwall's lemma, which gives you it gives you uniqueness at least for Wasserstein gradient flows. And let me write it like this. Okay, so imagine that you have, so dt mu is equal to minus grad L of mu t. Sorry, let me put a mu t. And similarly, dt nu is minus grad L of nu t. And the reason I call them mu and nu is that they might have different initial conditions. Okay, that's the difference between them. So the distance between what you get after time t from different initial conditions is controlled by e to the c times t times the Wasserstein 2 distance between the original ones. The initial condition you had for one and the initial condition you had for the other. Okay, that's like a basic stability result for Wasserstein gradient flows, and it's as good as you can hope to have. It's what you have in one dimension for ODEs in general. Okay, so mu 0 is equal to the initial condition, and nu 0 here is the initial condition. So this is like a general result. And let me tell you 3 consequences of this result and what they mean for neural networks. Okay.
The optimizer of the L1 neural network, because the right-hand side seems to not depend on mu, right? And the example number 3.
Yes?
It does depend on mu? The derivative is...
That's mu? And that's a fixed thing. This is the thing that generated your labels.
Down, you have the derivative of mu is equal to the optimizer.
Sorry, I just mean that what you get when you do Wasserstein gradient flow for this objective function is exactly the dynamics on the empirical measure of a one-layer neural network you would have gotten if you had done gradient flow for that neural network. I'm just reading the results backwards. I'm saying that's like a way of interpreting the right-hand side as something that wasn't obviously related at first to, yeah, right.
Thank you.
Yeah, Okay, so there's a universal constant, which depends on the initial mu naught. And
It's going to, the right is negative.
what?
C is negative.
C is negative.
No. What are you talking about? If you have 2 different initial conditions, the things get exponentially far apart from each other. It's an upper bound. It's a Gronwall's lemma, but for Wasserstein gradient flow. No. It would be great if it were negative. No. It's definitely not in general. You just it's basically saying if I how far do I get at time t if I have slightly different initial conditions? Well, it's at most exponentially bad, which is kind of as much as you can hope for. Yeah, okay. It just kind of is what it is.
Yeah, and W2 mu t can become really large. That's what you're saying.
Yeah, exactly. But in particular, so okay, this is going to be the first thing. If mu naught is equal to nu naught, then it's always 0. So that's like uniqueness, right? So in particular in the neural network world, if I define mu t bar to be any a priori just any weak limit as n1 goes to infinity of mu n1 t. Right? I say I'm training my neural networks. A priori, I don't even know if a limit exists. So I just take any weak limit. This immediately says that this limit is unique. And so you just have a deterministic solution. Okay, so in particular, e.g., mu t bar is deterministic. So at first in a neural network, your empirical measures are random, right? At the start of training, each of the weights is sampled at random, and so you have a random empirical measure. But the point is that because as the number of neurons goes to infinity, your random empirical measure just converges to the distribution for which you sampled. In fact, the trajectory of the empirical measures that you have at time t is deterministic. It just satisfies a deterministic nonlinear differential equation in the space of measures. So that's nice. You know that it's not random. Okay, and I'm going to use that hopefully to great effect in just a moment. But let me take a detour and say a second thing, which will be useful. So this is saying that in the limit, the dynamics of the empirical measures that you get for neural networks are some interesting deterministic dynamics. That's cool. But moreover, this thing gives you a rate of convergence, right? If you want to know what's the Wasserstein-2 distance between the dynamics you had on the empirical measure at time t at a finite width and at infinite width. So they're both solutions to the same Wasserstein gradient flow equations. They just have different initial conditions. Mu t bar satisfies that its initial condition is the deterministic measure from which you sampled the weights. And this initial condition is, okay, the random version of it, okay, the finite sample version. But still, you get that this is big O of e to the constant times t times 1 over square root of n1. Okay, and the reason is that the Wasserstein distance between a population distribution and an IID sample from it is like 1 over root n. Okay, so right away, you get that, in fact, if you have an actual neural network at some finite size, the dynamics you're going to get on the probability measures over the weights is close, in the Wasserstein-2 sense at least, the dynamics you're going to get at infinite width. So your limit didn't lose all the information that you were hoping to. And okay, a priori, it's only going to be okay over finite time intervals. That's just how the bound works. Okay, so that's nice. So you kind of get a rate of approximation. Rate of approximation. And again, your rate of approximation is really a dynamical one for the whole trajectory of optimization. So that was pretty cool. Okay, and now let me kind of combine these two and use them for something slightly less obvious, but I think quite useful anyway. And then I'll stop. Sorry, this is big O. This is all big O. I'm saying there's some implicit universal constant, and then you get something which a priori can be exponentially large in t, and then 1 over root n. Okay, so here's my third one, or maybe I'll just use this. Okay, so to use this, to use 1 and 2, let me now connect to these McKean-Vlasov kind of pictures or interacting particle systems. Okay, so let's recall my notation. So I had theta it was just the weights going into the ith neuron and the weight coming out of the ith neuron at time t. That's just what I meant by the ith version of my parameters. Okay, and note, so I'm going to write the conclusion, and I'll do an example of this for you, that when you write down the time derivative of the weights going into and out of the ith neuron, it's going to have the following functional form. I'm going to do this explicitly in a second, but this is the punchline. So it's some explicit function which depends on the current state of that particle or the current state of that neuron. I think of the weights going in and out of a neuron as its current state. And of course, it depends on all the other neurons as well, but it only depends on them in a mean field sense. Okay, it only depends on all the other neurons through the empirical measure. Okay, and that has to be true because all the neurons are exchangeable, but we'll see it exactly right now. So e.g., let me work this out for the first layer weights. Right, if you do d by dt of w1 it, what do you get? Well, okay, so this is minus eta times the width times the gradient with respect to w1I of the loss at time t. Okay, very nice. So is there a question? Oh, okay, very good. So let me plug in my loss. I'm going to take some empirical loss, minus eta n1 gradient with respect to the first layer weights. I have the sum on I goes from 1 up to n of, let's say, some loss function, little l, of the output on the ith example at theta t minus y. Okay, not minus y, maybe just comma y. It doesn't matter. Okay, so let me go over to the other board. You can try to beat me to the calculation if you're that kind of person. I always like to do that as an undergrad. Beat the professor to the answer. Invariably get it wrong and then embarrass myself by proposing the wrong thing. Okay, never failed to work. Okay, so let me just finish this calculation. So we get minus eta n1. Nice. And I just get the sum on I goes from 1 up to little n. And I get the derivative of the loss with respect to the output, doesn't really matter what it is, to xi theta t minus yi, times the derivative of the model with respect to the weights. So I'm just going to do it 1 over n1, sum on I goes from 1 up to n1. I get w2i, I get sigma prime of w1 it, sorry, all of these are its, dotted with x, and then I get an x I, oh my god, let me call this a j, this is a j, this is a j. Okay, the point is it doesn't really matter. When you just look at the structure of the derivative you get, I took the derivative with respect to the ith weights, and the ith weights, of course, appear. Ignore me. It's okay. That wasn't there. Okay, there we go. That looks better. So the ith weights appear, and then, of course, all the other neurons appear, but they only appear through the values of the output of the network. And the output of the network depends on all the neurons only through the empirical measure. Okay, so this n1 cancels with this n1. That should have been an n1. And you get minus eta, okay, times some stuff, times some function, which depends on theta it, like I said, and it depends on the empirical measure that you get at time t. Okay, and similarly, you can do the second layer weights.
So where did J come from?
Oh my god. Sorry, this should have been a J. I had too many indices that were called I. I was the neuron index, J was the data index. Sorry, thank you. Yes, I apologize. So it happens when I don't follow my notes carefully. Okay, so but let me just write the conclusion, then I'll pause for a second. So what do we learn? Right? So a priori, the difficulty of analyzing the dynamics of what happens is you could not separate it into what happens in each neuron separately. I mean, all the neurons are coupled. That was the whole point. That was like the difficulty. Like, the dynamics of the ith neuron is not autonomous because all the neurons participate here. But now look at equation 2, or estimate 2. Right? Estimate 2 says that the empirical measure, when you combine it with 0.1, is actually close to a deterministic measure. Okay, so without belaboring it too much, this is just equal to f with your empirical measure replaced by a deterministic measure plus an error, e to the ct 1 over root n1. Okay, and now what you find is therefore at large width, at least if the width goes to infinity but your time horizon remains fixed, the dynamics of all the neurons are independent of each other. Okay, so this is sometimes called propagation of chaos. Propagation of chaos. And the way to think about it is, remember, every neuron's parameters were initialized independently. And then they all started talking to each other through the training dynamics. But I'm telling you that what you win by going to infinite width, from the point of view of studying the dynamics, one of the things you win, is that actually each neuron actually enjoys independent dynamics. The randomness is only through the initial condition, and the dependence on all the other neurons goes away. It's replaced by this deterministic dynamics on the empirical measures. Okay, so from the point of view of the neurons, each neuron enjoys exactly the same dynamics in law. You randomly initialize it, and you train it by this equation. You just forget about this thing, where here you plug in the deterministic evolution of your infinite width kind of thing. Okay, so that's kind of really beautiful. Okay, so that's very cool. Let me stop and ask for comments and questions before I go on. I have a couple more minutes, but not much more. Yeah.
You can have access to the data. If you have
Say again?
Can you control that dynamic from data? Numerically?
Yeah, 100%. Yeah, of course. And indeed, this is now easy to simulate. This is just finite dimensional dynamics. It's just the ODE with random initial conditions. So you sample to your heart's content, you run your favorite numerical solver, and you'll see that this agrees rather nicely. Yeah.
If you were in yesterday's regime without the gamma being
Yeah.
then what would we see?
Okay, so what you would see is the following. I'm about to explain this right now. That's the last thing I think I have time for, but just in a word, you see, the way I've set this up, you can kind of tell, both the weights in the first layer and in the second layer move. The whole empirical measure moves as I do my training. In the previous regime, what's actually going to happen is the first layer weights will not move at all in the infinite width limit, or they'll move only a little bit. It's not totally fair. And the second layer weights will move much more. Okay, so so in that sense, you're going to get a totally different dynamics on the empirical measures. And you really won't get this kind of nice description of it. It's like some other kind of scaling limit. Yeah.
So in practice,
yes.
when you do optimization, you're going to see some sort of discretization of this.
Yes.
Right? Is it not the case that this fact actually spoils all the fun? Because like in the world of sampling,
yes.
you see people should look at Wasserstein gradient flows, and the example 2 you wrote there is this gives the Fokker-Planck equation. I think it corresponds to Lange-Band diffusion. And at some point people were like, oh yeah, you can sample by using the Lange-Band diffusion, and that's all good. But then other people came in and said, oh, in practice, you discretize it, and the nice properties don't hold anymore. So
the answer is not in this case. You see, this result really tells you that the sampling is fine. So some of these Wasserstein gradient flows in particular, at least when you stay in a finite dimensional space, you see that the space here is fixed. It's the input dimension plus 1, and I'm not scaling that. So think of that as being 5. It's like saying, can I sample a measure in a 5-dimensional space? And the answer is yes. If I wanted to do it in an infinite dimensional space, the answer would be no. And because you reduce the dynamics on probability measures in a finite dimensional space, actually the sampling is fine. You really get good fidelity. It's just you may lose information at long times. That's the only thing that might happen. Just because your instabilities will kind of grow. Yeah. Was there another question? Oh yeah.
Maybe it's explicitly in your presentation, but so first of all, you do have a kind of a PDE for the limit, right?
Yes, yes, yes.
Because you have a differential equation for the regional Newtonian, so if you replace it on both sides.
Yes, you do, completely explicitly, that's right.
And you also, is there a kind of a diffusion, like in lots of diffusion, with this mu you had corresponds?
So okay, I forgot to say it, thank you. So the short answer is, it's a very degenerate McKean-Vlasov thing with a zero diffusive term. You see, the only randomness here is just the random initialization. So it's like interacting dynamics, but like there's no noise to kind of wash things out. And you could add noise, like if you just injected noise into your gradients. Sometimes people will do that, although usually not. You could recover a diffusive term if you like. Or people will sometimes approximate stochastic gradient descent as full batch gradient descent plus noise. And that noise would give you an interesting structured noise in your diffusive term that you would get. So there are various ways of injecting the noise and really making it an honest McKean-Vlasov thing. But for the moment, it's like this kind of weird, like driftless, diffusionless. That's what I meant to say. Yeah. Yeah. Okay. But in some sense, it makes it easier. In some sense, it makes it degenerate. I don't know. You tell me. Yeah.
What's wrong using on the fact that the initialization is Gaussian?
So we're just using it. The initialization is IID with like a first bounded moment. No, the Gaussian was just to fix ideas. That's true for you. I'll say for you. That's right. That sounds better. Yeah. Question. Okay. So I have just a couple minutes. So let me kind of address Michele's point a bit. It's something that I think was a bit confusing to people for a while, but there's now kind of a very simple way of understanding. The reason that I wrote the introduction the way I did is I just wanted to make it seem as implausible as possible that we're going to get a different answer between the NTK regime and the mean field regime. Because they look essentially the same, but we got completely different answers. And so the question is, what happened? Is there any feature learning? What is supposed to happen? So let me try to say something sensible about that. So NTK versus mean field. So there's an extremely simple calculation that you can do. And it goes like this. So to understand the difference, so let's just introduce a notation for what the first layer neurons see over time. Okay, I'm going to write H, I, T of X. That's just going to be my definition for W1 IT dotted with X. Okay, so it's just the input to the ith neuron after T time in optimization from input to the network that I call X. Okay, so here's a kind of repackaging of what I've already written, which is a useful repackaging, I think. So note the following. So if you can just explicitly write down the differential equation that H satisfies. I mean, just because you differentiate the W, and I already have the answer, okay, somewhere secretly over here. So here's what I get. When you do the calculation out, you get minus eta gamma over square root of n1 times the sum on, let's say, j goes from 1 up to little n over your training data points of the second layer weights you have times sigma of your first layer weights dot xj times you have x dot xj, and then you have the residual times z2 of xj theta t, sorry, there are t's here everywhere, minus yj. Okay, so you just get some explicit formula. It's not extremely important what formula you get. Here I've assumed the L2 loss. This is the residual of the mean squared error. So I've just taken a particular loss because I didn't want to rewrite this term up here. But that's not the important point. Okay, the important thing I want to focus on is when you do this calculation and the dust kind of settles, you just have this prefactor. Okay, and what do you observe about this prefactor? Say again? So it's constant for mean fields, but what happens to it in the NTK setting? When n1 grows? Okay, right, indeed, thank you. Okay, so here's the point. The key observation is that if gamma is little o of square root of n1, if you take anything below this mean field scaling, then the first layer weights change very little, or these h's change very little. Okay, each one of them, in particular if gamma, for example, is just 1, changes like 1 over square root of n1. Okay, now there's n1 of them. You know, so just because every one of them changes a little doesn't mean they don't affect the output at all. But that suggests to you that you should be able to linearize with respect to the change in the first layer weights. Okay, and that is exactly the NTK regime. You can just consider only the first order change in the first layer weights and neglect all higher order terms. But, okay, if gamma is equal to theta of square root of n1, then the first layer weights all change a lot. Okay, and in this one layer setting, that's kind of the hallmark of feature learning, right? Quite literally, the output of your network is a linear combination of some potentially learned feature functions. Right? I'm telling you, if the inputs to the sigmas change a lot during training, then you've learned interesting data-dependent features. Okay, you just kind of see it staring you right in the face. And if the inputs to sigmas don't change, or more precisely, their change is dominated by just the linearization of the change, then they just, by kind of taking the linearization into account, you don't get any feature learning. You just have some fixed set of features, except it's not the sigmas, but it's the linearization of the sigmas around the start of training that you get. That's kind of the NTK scaling. Okay, so this, in a sense, is like at the heart of the difference. And people have worked out, using these kinds of ideas, how to do mean field scaling, at least, for deeper neural networks. I presented everything in this lecture for one-layer networks. And the reason they wanted to do it is they wanted to set up optimization in such a way that every neuron, what it sees at every time, changes an order 1 amount. That was their heuristic for how to make feature learning happen. The way we initialize the network, if you remember from the Gaussian process limit, every neuron is some order 1 random variable. That's what it sees. And if you want feature learning to happen, or if you want something like feature learning to happen, they're not super precise about what they mean by feature learning, you at least want each neuron's pre-activation to move an order 1 amount in an order 1 time. That's kind of what the heuristic is, if you've ever heard of things like the mu-p parameterization or the mean field parameterization for deep networks. That's kind of what they're really trying to do. Okay, and that's the kind of calculation you have to do to at least guess the right answer. So okay, this is perfect. I'm right on time. I'm going to stop. I'm happy to take questions and comments on all of this stuff. Yeah.
One brief question. You mentioned that there are 3 consequences of the Grunwald's lemma. First, that the bar mu is deterministic.
Yes.
The second, about the rate of convergence. And the third, I didn't see the digit 3 appear on the slide.
Oh, sorry. 3 was really just my combination of 1 and 2. Yeah, sorry. I changed my mind. So you're correct. 3 never appeared, in fact. Yeah.
Is there another regime to indicate in film possible to get something there?
So, okay, the short answer is no, and the long answer is maybe. So I really think if your initialization, if the distribution of the W's just has lots of moments, it's not really possible to get anything else. This kind of analysis turns out to be extendable to at least order 1 time horizons. And there's just this threshold. You either get something interesting or you don't, more or less. But if you study things somewhat more finely and you ask, okay, you have this deterministic dynamics, either this mu t bar or you have the NTK dynamics, but you can ask, what about a central limit theorem? What's the dynamics for that? Then you can feel more fine scales, depending on how you set gamma. And I think, but I don't know, if you have heavier tailed W's at initialization, you might get a different set of regimes altogether, and I don't know what they are, in fact. So maybe. That's what I mean by maybe. Yeah.
So I'm just trying to get to a bigger picture.
Okay, yes.
So it seems to me, after the 3 lectures, we are mostly interested in the dynamics of gradient descent, what happens with that, what we're able to identify,
yes,
and so forth, right? And it seems to me that we might look in a completely opposite direction. So we envision something what this gradient descent is supposed to do, right? And for that particular sample we envision, I don't know, maybe is that the equation we want to get? Then we go back, what type of, fine-tuning we have to do with the model to achieve this effect. So it's a kind of vice versa. Now you presented it in a way, okay, in the first lecture, well, you get convergence to Gaussian process, and so the gradient descent does a linear thing.
Yeah.
Right? Well, in principle. Here, something else. If this happens, then something else happens.
Yes.
But we might look in the other direction,
yes,
because we're actually interested in static gradient descent. And then we have to understand how we need to fine-tune our model to get the right dynamics or whatever you can
yes.
call. And because it reminds me a lot of what people in SPDs or PDs are doing. They always, we have this model which nobody can show that it exists, so we try to simulate it. And then they're very clever. They say, well, it's very clear. We have to put the gamma 1 here of this order. Then, because we have this operators, and we have to put the gamma 2 here, and that's what you do here. So you put the gamma inside the Z2 and gamma squared inside the operator. It looks very kind of immediate to me. Also, of course, the operators you consider are very specific.
Yes.
In the SPDs or PDs.
Yes.
Much more involved, but so is it not the other way around? We have to look at this. So if you are interested in a certain dynamic for your gradient descent, let's look for a particular type of fine-tuning of the original neural network, which achieves exactly.
Yes. So I think the short answer is people definitely try to do that. I think they're both quite interesting, right? For me, the way I tend to think about it is something interesting works in practice, and I'd like to explain to myself what's going on. That's kind of this direction. But certainly, especially if you know something about your problem and you say, I'd like this to appear, but maybe for some numerical reasons it's hard for me to simulate it or hard to make it happen. Can you make a neural network that does something similar? That's like the inverse problem, if you want. And I think people do that, though I don't know much about it. That's the truth. So I think it's definitely a sensible thing to think about. Yeah. Yeah?
If you take the perspective of choice of gamma in the field as a kind of normalization, so you get the right weighting and the correct normalization for the neuron, is that the perspective that you can take to think about Batch normalization as well?
So the truth is, I don't know how to think about batch normalization in a principled way. I'm not sure anybody really does. Like, so I didn't quite say it this way, but indeed, you can derive this parameterization, where to put the gammas and where to put the n's, by asking that you want every neuron to have an order 1 pre-activation, you want it to change an order 1 amount in order 1 time, and you want the output to change an order 1 amount in order 1 time. Okay, that's like, you have some equations, you can basically solve those equations, and you figure out the parameterization. I don't know a similar thing for batch norm. Yeah. Maybe somebody does, but I've never come across it. Is that it? Yesterday people had more. No, I'm kidding, I'm kidding.
So let's thank